Glide 5-3 Glider Performance. Let us embark on a journey to unravel the complexities surrounding weight and balance in the enchanting world of gliders. This subject, paramount for the safe operation of these majestic aerial crafts, encompasses a pivotal concept known as the center of gravity, which influences the stability along the longitudinal axis of the glider. In our academic exploration, we discover that achieving an optimal pitch attitude handling in a glider necessitates the CG of the properly loaded craft to be situated forward of the center of pressure. Manufacturers, in their wisdom, provide explicit CG limitations for our adherence, meticulously documented within the glider flight manual or pilot's operating handbook. Should our meticulous equilibrium be disrupted and our glider find itself nose-heavy, challenges manifest during takeoff, demanding an earnest application of back pressure on the control stick. The ailment of nose heaviness may usher in tail stalls at unnaturally high airspeeds, coupled with a swift nose-down pitch inclination. A prolonged recovery period from stalls and the conundrum of executing landing flares represent the tribulations encountered. Alas, these issues may befall us if we venture into the forbidden realm of exceeding the maximum permitted pilot weight or whimsically installing superfluous seat or nose ballast weights. Conversely, as we traverse the theoretical landscape, encountering a CG aft of its designated limit heralds its own set of challenges. Tail heaviness, as we shall dub it, renders pitch control an arduous task, teetering on the brink of impossibility. The fundamental harmony between the horizontal stabilizer and elevator, designed to provide a delicate equilibrium, is disrupted. Our theoretical aircraft yearns for positive stability, whereby the craft instinctively rights itself after a perturbation. Alas, the harmony is shattered if our control surfaces find themselves in a stalled condition. Pragmatically, common culprits leading to a CG located aft of the permissible limits include a lightweight pilot without the necessary trim ballast weights, the unwitting attachment of a tailwheel dolly, the clandestine accumulation of foreign matter in the aft fuselage, or the installation of a non-approved tailwheel or tail skid. To unravel the mysteries of weight and balance, certain academic institutions, represented by glider manufacturers, endeavor to furnish us with graphical presentations. As we gaze upon the visual representation of our weight and balance envelope, we discern permissible weight ranges for occupants in both the front and rear seats. Our calculations unfurl, entailing the determination of moments for each component, ultimately ensuring that our total weight and CG remain harmoniously within the accepted limits. Thus, as we conclude our academic discourse, let it be etched in our minds that the meticulous management of weight and balance in our soaring vessels is not merely a theoretical exercise but a fundamental prerequisite for the graceful dance of gliders through the boundless skies. Let's explore the fascinating realm of ballast, a critical aspect in the aerodynamics and performance of gliders. Ballast, akin to a carefully orchestrated performance, plays a pivotal role in adjusting the glider's weight distribution and optimizing its flight characteristics. In the gliding domain, ballast is classified into two main categories: trim ballast and performance ballast, each serving distinct purposes in the complex interplay of aerodynamic forces. Trim ballast, functioning much like an instrumentalist fine-tuning their instrument, is employed to adjust the center of gravity of the glider. Typically composed of metallic weights, these elements are strategically placed within the glider structure to compensate for variations in pilot weight. This ensures that the CG remains within specified limits, allowing for stable and controlled flight. In some instances, seat cushions with integrated weights may also be utilized for this purpose, although their propensity to shift position warrants careful consideration. On the other hand, performance ballast steps onto the stage to enhance high-speed cruise performance. Water, acting as the medium for this performance, is loaded into designated tanks within the glider's main wing panels. This addition of weight optimizes the glider's operating weight, resulting in increased ground speed, a valuable advantage during cross-country soaring and sailplane racing. However, as we navigate through these aerial maneuvers, it's crucial to acknowledge the nuances and considerations associated with ballast usage. The introduction of water ballast, while beneficial for soaring conditions, brings about changes in takeoff and climb-out characteristics. Acceleration becomes more deliberate, ground roll extends, stall speeds rise, and aileron response undergoes subtle alterations. Before the final descent of our exploration, it's worth noting that water ballast is judiciously discarded before landing. This intentional shedding of ballast not only reduces stall speed but also contributes to a gentler landing approach, a shorter landing roll, and decreased structural loads during the landing phase. In conclusion, The symphony of ballast in glider flight demands a thorough understanding of its effects and a commitment to safety. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.